In manometer case, the open, sealed end, and the differential one. In addition to the board and gauge, we determined the pressure, but the pressure that we measured was gauge pressure. It means that we are calculating a pressure of a fluid without considering the effect of the atmospheric pressure. Usually, whenever you want to measure pressure in industrial application, you do not account for the atmospheric pressure. You add it later on to find the absolute pressure. Gauge pressure is measured relative to atmospheric pressure, while absolute pressure is measured relative to perfect vacuum. Say this is the absolute pressure. It is relative to perfect vacuum, P equal to 0, right? The gauge pressure is relative to the atmospheric pressure, which we know that it is greater than 0. I also mentioned the relation between the vacuum and the gauge pressure. If we saw a negative value of gauge, like if we go upward in a manometer, for example, the pressure gauge will be negative, which means the vacuum will be positive. That's the whole story between the vacuum and the gauge, and that's the whole story about gauge, absolute, and atmospheric pressure. Now moving on to this important word, which is the concept of mole, which is related to mass. A concept that's really appreciated by chemist people because it makes their life easier. They deal with molecules, and we as chemical engineers also deal with molecules. It's harder to say that we have billion molecule or 10 to the power 23 molecule. No one will ever listen to you if you said, I have 10 to the power 23 molecules. I have 10 to the power 39 molecules. How can I shorten it? How can I make it fancier? Only 1 mole describe 6.02 times 10 to the power 23. Scientific notation. 3 significant figures. And this number is Avogadro's number. You might find it weird when I start talking about these very large numbers, but this is because real-life products contain at least this number of molecules. The simple relation that is meaningful, like the previous video, degrees Celsius. Now this one, moles, 6.622 times 10 to the power 24 molecules. Material contains this number of molecules, or 11 moles. Short story. And to convince you further, maybe moles cannot be enough to shorten the number. Especially in industrial processes, the production rate could reach to a scale of 1000 mole. So we will shorten it by kilomole. That's why we need the concept of mole, and then related to the concept of prefixes that we discussed in the first video. Mole is an SI unit, and because we have an SI unit of moles, then it means we have an American unit of moles, which is pound mole. For the SI unit, it's moles. The nice news here is the fact that the relationship between mass, if you recall, 1 kilogram, it's the same as if you have 2.2 pound mass. If you say 1 kilomole, it's equal to 2.2 pound mole. This is not just a coincidence. You might ask me, is it possible? I will say yes, it is possible. And this is by introducing the concept of molecular weight that will relate mass to the mole, and then we will end up having exactly the same 2.2 pound mole for each kilomole. A molecular weight of M has the dimension of mass divided by mole. Either kilogram, pound mass, mole, kilomole, whatever. If I want to reach from pound mass to pound mole, write 2.2 pound mass, and then if this is an American system, this M will be here. I want to take the reciprocal because I want the unit of mole per mass to cancel mass with mass. This 1 over M will have the unit of pound mole divided by pound mass. This is the conversion between 2.2 pound mass to pound mole. And here we have 1 kilogram in the bottom as this relationship, pound mass per kilogram. Remember, we want to cancel pound mass with pound mass, like this one. And we want to cancel kilogram with kilogram to end up having, using molecular weight, pound mole per pound mass. So you will notice that we will cancel also M with M. When you use mole and mass to convert from one system to another, the factors will be the same. 1 kilogram, 2.2 pound mass, 1 kilomole, 2.2 pound mole. If this M for carbon, I'm sure we have chemistry people looking, so they will be proud. Carbon is the door for the organic chemistry, and it has the molecular weight of 12, starting with the unit pound mass divided by pound mole. 2.2 pound mass For 1 kilogram conversion factor, I need to divide by 12 pound mass with pound mass. You know that also the mass of the carbon will be 12 kilogram for 1 kilomole. We'll put 12 in the numerator. You will cancel kilogram with kilogram. You will cancel pound mass with pound mass. The magnitude of the m, in this case 12, will be cancelled with the magnitude of 12, regardless of the unit type. Pound mass per pound mole, kilogram per kilomole. 2.2 pound mole divided by kilomole, which is the same as 2.2 pound mass divided by 1 kilogram. Just for the sake of respecting science, when I actually say molecular weight, then it means only this number, 12. It doesn't mean the unit, but I'm assuming that the molecular weight and the molar mass are the same concept, but actually they are different. Molecular weight is just the number, molar mass is the number plus the unit, but I'm assuming that they are the same. With that being said, I'm relieved because I didn't commit a serious crime to science community. We'll keep referring to molecular weight if we have only a single element. But if we have a component like carbon dioxide, the criminal that's responsible for the global warming, it's not an element. An element consists of only one single atom. Compound consists of many atoms together or many elements together. Carbon with oxygen and with another oxygen. Element and compound cause us to define what we call atomic weight. It is the same as the molecular weight if and only if, a condition that math people use, if we are dealing with only a single element, atomic weight and molecular weight will be the same. If we are dealing with a compound, consider this example, carbon dioxide, the atomic weight of carbon is 12. You see, when it is only carbon, we will say molecular weight of carbon, which is the atomic weight. But if it is involved with another element, it will be the atomic weight. Add to it the atomic weight for oxygen, 16. And because we have two oxygens, we will add another 16. The answer will be 44. The atomic weight now has a unit of atomic mass unit relative to only one atom. And guess what? This is equal to 44 gram per mole equal to 44 kilogram per kilomole equal to 44 pound mass per pound mole. Because our subject here is to understand the definitions rather than proving them, let's define each one of them. The atomic mass unit AMU is a unit of mass. 1 AMU represents the mass of a single proton is equal to 1.6605 times 10 to the power minus 24 gram. It is the unit for the atomic weight, depends on what we call isotope. A single element could have 3 forms, like the case when we have carbon 12, carbon 13, carbon 14, with different number of neutrons. And if you average them together, depending on their percentage of abundance, they will give what you will see on the periodic table, 12.01 AMU per one atom, or 12.01 gram per mole, for example. That's the whole story about atomic weight, at least in my case, because I will move to the thing that I was aiming for in the first place. If you have 100 gram of carbon dioxide and you want to find out how many it has in terms of mole, if you see the periodic table, you will see 12.01, you will see oxygen 15.9994, make it 16. You will say the molecular weight will equal to 16 times 2, because we have 2 oxygen, plus 12 carbon, and the answer will be 44 AMU, or because we want to convert from gram to mole, we will say gram per mole. This is the first requirement. Now use conversion factor. Molecular weight can be a conversion factor. We know 44 gram for each 1 mole of carbon dioxide, 2.27 mole carbon dioxide. Now imagine you want to find the value in pound mole. We need to convert it to kilomole. We have the relation of pound mole with kilomole. 1000 mole equal to 1 kilomole, prefixes, and 1 kilomole is equal to 2.2, like what we have found before, pound mole. Answer is roughly about 5 times 10 to the power minus 3 pound mole. Something interesting now, number 3, how many mole of carbon, not carbon dioxide. We do know the mole of carbon dioxide. We don't know the mole of carbon. 1 mole of carbon dioxide contains only 1 mole of carbon. The answer should be 2.27 mole of C. Don't say that always mole of C is equal to moles of carbon dioxide. Here, just because we have coefficient of 1 and here we have only 1 carbon, that's why we said they are equal. If you want to be convinced, number 4, you want to find the mole of oxygen now. And you do have 2.27 carbon dioxide. 1 mole of carbon dioxide is now equal to 2 moles of oxygen. So you will cancel mole of carbon dioxide, and you will get 4.54 mole of oxygen only, not O2. Moving on to the 5th case, you want to find the mole of O2 now. The mole of O2. If you do have 2.27 mole carbon dioxide, and you want to find the mole of O2, not mole of O only. 1 mole of carbon dioxide contains only 1 mole of O2. This is a very big difference between this point and this point. I'm asking for mole of oxygen atom. Here I'm asking for mole of oxygen gas. Cancel, and the answer will be 2.27 mole of O2. Now let's do a plot twist. If I want gram of O2 and gram of oxygen, if you do know the mole of O2, use it to convert to gram of O2. 2.27 mole of O2. You do know the molecular weight of oxygen gas. 1 mole of O2 is equal to 16 times 2, which is 32 gram of O2. And the answer will be 72.64 gram. If you want to find gram of oxygen atom, then you will use moles of oxygen atom. 4.54, you know that 1 mole is equal to 16 gram of oxygen. Cancel. 72.64 gram of oxygen atom. Here gram of O2. The wonderful and tedious situation is number 8. You want to find out what is the number of molecules of 2.27 mole of carbon dioxide. You know that 1 mole only of CO2 is equal to 6.02 times 10 to the power 23 Avogadro's number molecules. And the answer, 1.37 times 10 to the power 24 number of molecules. By the way, this is not only for molecules. You can also say 1 mole is equal to 6.02 times 10 to the power 23 ions, which is equal to 6.02 times 10 to the power 23 molecules or atoms. You might even see it in ions or atoms, depending on the type of bond. But let's not open the door of real chemistry and just consider the basic chemistry skills that we need for engineering, especially in mechanical, chemical, petroleum engineering. Even though we converted so far mass and mole amounts, this story can also be applied to mass and molar flow rate. The same concept, the same conversion factor. But whenever you write a certain number of mole or mass, you write it in terms of a certain time, whether it is second, minute, day, year, depending on the problem. All of the things that I said so far also included a pure component. I'm talking about only one single compound or only one single element. I'm not talking about combination of compounds together. However, in small scale and large scale production, rarely you will have only one single compound or one single element. And many cases you will encounter the situation of a mixture containing more than 2 compounds or 2 compounds if you are lucky. A small container, because we recently have COVID, hand sanitizer. Usually hand sanitizers contain water plus alcohol, mostly ethanol or isopropanol, but let's generalize it and make it alcohol. It has generally 80% of what we call composition, and water the remaining, which is 20%. It's about this percentage. This composition allows you to find the amount of the alcohol stored inside the hand sanitizer. If you multiply 100 gram by this composition, you will find the amount of alcohol inside the hand sanitizer, which will be in this case 80 gram, and the remaining will be 20 gram of water. This composition could be composition coming from mass. If you refer to it by weight or by mass, you will call it mass fraction. Mass fraction of alcohol is 80%. The mass fraction of water is 20%. The mass fraction multiplied by the total amount of hand sanitizer that represents both of these components will give you the amount of alcohol, and the balance or the remaining is 20 gram of H2O. Can we in this case open the door to the mole and relate them to the mass in order to find out what is the amount of hand sanitizer contained? And the answer is yes, and it is actually the door to the 15th rung, by finding what we call average molecular weight. It is not only about one molecular weight, it is the average molecular weight that is composed of the molecular weight of alcohol and the molecular weight of water. It turns out that we really need mass fraction in order to find the average molecular weight, which means it will be by mass, by weight. Because you plugged mass fraction, then you will have average molecular weight for mass. And the unit will say gram per mole, because we have 100 gram. Using mass fraction through this equation, 1 over the average molecular weight will be x. If it is mass fraction, we'll call it x. If it is mole fraction, we'll call it y. Add to it mass fraction of water divided by molecular weight of water, 0.0285. Flip it and then you will find the molecular weight. It's 35. When do you know that you are correct? If you see that the average molecular weight is between the molecular weight of alcohol and the molecular weight of water, which it is 46 and 18. Furthermore, 35 gram per mole has to be close to 46 gram per mole, which is the molecular weight of ethanol. The reason is because the portion of the alcohol is higher than the portion of water. The average molecular weight will be a little bit closer to 46 gram per mole, and as I said, this is by mass. Now use this as a conversion factor. You will find the value in terms of mole. 2.86 mole of hand sanitizer inside the container. If I ask you, can you find what is the mole fraction of alcohol and water? It should be easy, supposedly. There is a relation that says the average molecular weight by mole. It will be, because it's mole fraction, we say y, of alcohol multiplied by the molecular weight of alcohol. Add to it y of H2O multiplied by the molecular weight of water. We have the molecular weight of water, we have the molecular weight of alcohol, but the problem here is the fact that we don't have either alcohol fraction and water fraction in terms of mole, because we have two unknowns with one equation. But there is a fact that I said before, for a system composed of two components, like the case here, I've said 80% of alcohol and the remaining should be water. If the story is applied by mass, then it should be applied by mole. Then y alcohol should equal to 1 minus y of H2O, because they complete each other. Alcohol mole fraction plus water mole fraction give us 1. If you substitute all the numbers and you solve for y alcohol, 35 gram per mole minus 18, which is the molecular weight of water, divided by 46 molecular weight of ethanol minus 18, and the answer will be 0.61. Now, because I said that y alcohol equal to 1 minus y H2O, then it means immediately the balance is equal to 0.39. A quick recap: we used the mass fraction with the total solution of hand sanitizer to find the average molecular weight in terms of mass by weight. We took this mass by weight, used it as a conversion factor to convert from gram to moles. We took it and then used it along with the molecular weight of the pure component of alcohol and water to find the mole fraction of alcohol and water. But you will not find your way if you have more than two components. Imagine if you have here another term. You will say y1 plus y2 plus y3, because you have three components, for example, will equal to 1. And then you say y1 minus y2 minus y3 is equal to y1. So you will have two unknowns inside one equation. So this story can be applied only when you have system containing two components, or what we call binary system, which has only two components. If you have this case, then you will call it tertiary system, because you have three components. If you are able to convert from mass to mole, which is the whole story that we have been talking about in this video, if you can convert the molecular weight of mass to molecular weight of mole, then why don't you convert mass fraction to mole fraction? Making the story complete, we write the name of the component, ethanol, water. Another column that contains the mass fraction. Usually mass fraction is given 80%, 20%, and then you write the mass, and then molecular weight. If you notice, molecular weight for pure component, it doesn't have by mass or by weight. The average molecular weight has its value in mass or in mole, and then moles. Lastly, mole fraction. Now we are stuck here. We need to find the mass. We have the total mass of the solution, which is 100 gram. We'll call it the basis. What you are calculating based on is what we call basis. The basis could be also 1100, my favorite number. So regardless if you are given the value or not, use any basis you want. 1100, 11,000, 1100, 15,000, the answer will be the same. But if you are choosing basis of 100 gram, then multiply this 100 by the fraction 80, because we said gram, here 20 gram. The molecular weight of ethanol is 46 gram per mole, here 18 gram per mole. The moles, now you just divide 80 by 46 to cancel gram with gram, 1.74, and here is 1.11. Now take the mole fraction. How do you find the mole fraction? Mole fraction of H2O is equal to the moles of H2O divided by the total solution, which is moles of H2O plus moles of alcohol or ethanol. Do this formula now. 1.11 divided by 1.11 plus 1.74, and the answer is roughly 0.38 or 39. And the balance is ethanol, so Y alcohol is equal to 1 minus 0.38, which is equal to 0.61. The same answers, but shorter time and efficient, and also can be applied to whatever number of components you have. Binary, tertiary, 4, 5, 6 components, whatever. Later on, these conversion techniques will be needed, and they will be the start for finding other complicated process variables in terms of what we call material and energy balances. So it's better to have a strong foundation early on. To keep things more interesting, if you have the volume and then you divide it either mass by this volume, then you will have density, as we know, or you divide mole by this volume of solution. It will be called concentration, C capital. This is called actually mass concentration. This is called molar concentration. Why? Because we are describing the mass of a sample in terms of a volume of solution, and we are discussing mole of a sample per volume of solution. Once you have concentration or once you have density, then you can relate them to mass if you have density. You can relate them to mole if you have concentration. And remember when I said specific volume could be for mass or for mole, if you recall I said 1 over rho is equal to specific volume. Now 1 over C is also specific volume, but usually when you say specific volume we refer to this one. But let's not ignore the molar concentration as well, and it will be one of the factors that you will rely on and use it in order to find the amount of mole or the amount of mass. And this means that specific gravity that we discussed before is also important, because it allows us to find the density, allowing us to find mass, allowing us to find the mole. So story is all related, but we introduce it little by little. And later on, when you see the processes in the future, you will combine all of what you have taken in order to apply it in a certain chemical process or physical process. Speaking of, we will discuss one of the fundamental concepts that we need in chemical engineering basics: material balance and energy balance. And all what we have taken before in the previous videos were the introduction to these two important concepts that are used extensively whenever we want to design or operate a certain chemical or a physical process. One of the terms that we need as well is an extension to the story of mass and mole fraction. Some mass and mole fractions will be very, very small, like the story of moles and like the story of degrees Celsius. We want to make it fancier. A concentration of 15 times 10 to the power minus 6 could be the mass fraction, could be the mole fraction. And so we want to find a fancy name that replaces this number by something simple. This is the concept actually of parts per million and parts per billion. Now it will have a unit. Instead of having this dimensionless number, mass fraction or mole fraction, you will have 15 parts per million. You are a person who were born, but you are not the only one in the world, because we have approximately 7.5 billion people. So you represent one out of these 7.5 billion people. If you want to make it fancier, multiply by 10 to the power 9 and the unit will be parts per billion. Rather of writing 1.33 times 10 to the power minus 10 mass fraction or mole fraction, you will write it 0.133 parts per billion, just only 1 over 7.5. In the next video I will talk about what I have talked about today and in the two previous videos by solving examples.